Hello, everyone. My name is Krishna Mehta, and I welcome you to the webinar when we ask generative AI to build a credit risk scorecard. Joining me today in the panel is our co founder, Pat Bhattacharya, and senior data scientist, Shikha Agarwal. Due to the large number of participants we have had for this session, this webinar will be a little less interactive than some of our other events, but our presentation should wind up in about 30 to 35 minutes, and then we will take questions. So please feel free to add your questions to the Q&A tab as the presentation goes along, and we will answer them all at the end of the presentation. A little bit about us. We are a data science company. We are based out of New Jersey. We have a presence in India. We help organizations make better business decisions with the use of predictive analytics, machine learning, and AI. We serve financial services clients of small to medium size. Uh, we serve a lot of companies in the publishing industry. We work with a lot of nonprofits, and we also do some work in retail. Over the years, we have been very fortunate to be able to solve some very interesting and challenging problems for our clients. Here are some brands that have trusted us with their projects. Let me tell you a little bit now about the experiment we did this for this project. So, we have all grown up reading the story about Snow White and the magic mirror, magic mirror, magic mirror. So it was like, I think it went something like mirror, mirror on the wall, who is the fairest of them all? And guess what? Now we have a magic mirror called uh, generative AI, and we ask it questions and it answers. So our experiment was GenAI on the cloud. Who is the riskiest of them all? So that's like the first part of the experiment. Let GenAI tell us what's risky, who is risky and who is not. And we compared that uh, with the traditional credit risk model development. Over here, you have to go through the whole 9 yards. You have to treat data, you have to do some feature engineering, then you have to do model development and you have to make sure the model is stable, and then finally you validate the model on another sample. So this was the comparison. In developing the credit risk model, we put it to the rigor and made sure that if the model was, say, audited, it would pass all the audits. So we compared that to the Gen AI model. We chose logistic regression for that because in a lot of audits that works well. The results will show are with logistic regression, but I will tell you, we have done similar experiments with XGBoost, and they are in line, similar. We just didn't take them to the level of rigor we took our logistic regression model. My colleague Shikha will take you through the details of the AI experiment, but before handing over to her, I wanted to talk a little bit about data security. So here I was, reciting Gen AI on the cloud, uh, and I'm sure the data security folks and the legal folks were thinking, hey, does this mean now we have to expose our data to the cloud? The answer is no, you don't need to do that. A lot of the GenAI models can be downloaded and deployed on the local GPU within your server. Your servers have to be GPU enabled, but then you can download it within your infrastructure. That means that now there is no external data transfer. You don't have to upload your data to the cloud, and it ensures everything is on premise and data is secure. Now, the way this works is you download the model, it's a static version, and then it's you slowly train it and make it learn with your own data. So it's becoming more and more focused towards your problem. Now, there might be some situations where you might say that, hey, it benefits me to learn from the cloud and from the multiverse, in which case, but you have the data security issue, in which case you could periodically download this model and retrain it with your local data. So just wanted to bring this up. And with that, I will now hand it over to Shikha, who will take you through the details of the AI experiment.
Thank you, Krishna. I am Dr. Shikha Agrawal. As Krishna has mentioned that we are experimenting with generative AI to explore its potential in creating credit scorecards. So let's discuss first what is generative AI and from where it comes from. To discuss this, first we have to understand what is artificial neural network. Artificial neural network are the machine learning model which mimics the way human brain works. It has one input layer, one hidden layer and one output layer. An artificial neural network with more than one hidden layer are called deep learning models. It has the capability to learn complex pattern from complex data set. A deep learning model with a attention mechanism is called transformer. Attention mechanism helps the model to learn to focus on the important part of the input by assigning weight to the input. Uh, Assigning weight to the input. In this way, transformer model give more focus on the part of the input which has higher weight assigned to it. Transformer models can generate two types of outputs. Some transformer models can generate prediction, can perform prediction, and some transformer model can generate new content. A transformer model which are capable of generating new content are called generative AI models. Like ChatGPT and Llama models are the generative AI model which can generate new text. Similarly, DALI and the stable diffusion models are the generative AI model which can generate new images. The generative AI model which works on the text are called Llama model, large language model. ChatGPT and Llama models are large language models which works on text and can generate new text. So in this experiment we are using the Llama model, which is a large language model, and we are using it for the prediction. Before we go deep into our discussion, let's discuss about some LLM model which are designed for financial services and popular in this field. The first model I would like to talk about is Llama model. Llama models are designed by the Meta and they are designed for natural language processing and generation. The important feature of these models are its high performance with reduced computational requirement as compared to other LLM model. So we are also using this model in our experiment. Why we are using this in our experiment we will discuss in later slides. The next model which is popular in the financial services is Finbert, which is developed from the BERT model and it is used for sentiment analysis. The Flang model is for the report generation and summarization. Fin GPT model can generate human-like text with financial insight. CALM is derived from the Llama model and can be used for financial application. FinMA is popular in the field of market analysis. Instruct FinGPT can answer the queries related to the financial services. Bloomberg GPT is fine-tuned using the Bloomberg financial dataset and can be used for forecasting. Invest LLM can be used for invest management, and FinLama can efficiently handle the financial processing related to natural language financial processing. Now let's discuss why we are using Llama 2 model in this experiment. We have conducted a literature survey on LLM model in the field of financial services, and we have found that Llama model generally performs better than other financial LLM models. To check the resource consumption efficiency of Llama 2 model, we have conducted an experiment between Llama 2 and Llama 3 and found that Llama 2 is not only faster but also lighter on resource consumption. This is good for organizations that want to maximize efficiency while minimizing cost. To data security, we have seen that Llama model can be downloaded and deployed on the local GPU within the organization server. This setup ensures that sensitive financial data remains secure and reducing risk associated with cloud-based consumption and deployment. Now let's discuss how we have used Llama 2 model in this experiment. In this experiment, we have used Llama 2 model to generate two output. First output is the prediction and the second output is the generation of embedding. In this slide, I will explain how we have used Llama 2 model to generate the prediction. To perform the prediction, we have fed the Llama 2 model with sample classification for learning. The sample to perform this feeding, we have given query to the Llama model. The query has three components: the task, the examples, and the text to which Llama model will respond as prediction. The task part defines the goal that classify customer credit worthiness as either good or bad. The example part guides the Llama model how to classify the input attributes into good and bad. So we are giving one example for each class. Next we have text. It is the text to which Llama model will respond, and the structure of this text is similar to the examples that we are giving in this query. So Llama model will analyze and respond according to the examples given to it. So we are feeding the queries for each record into the Llama model, and we are performing this process iteratively until all the records are fed to the model. Then finally Llama models are giving the response for each record. So we have prediction for each record after the whole process. Another output that we are generating from Llama 2 model in this experiments are the embedding. So how we are getting embedding? We are feeding the query to the Llama model, and Llama model is generating the large numerical representation of this query. So this large numerical representation of the query is called embedding. Suppose a query has a question about car, then the embedding for that question will be like other text about cars. These embedding can be extracted and can be stored and can be used in a project. In this project we have 14 predictors and the embedding size is 35,000. So we are using this 35,000 embedding in our experiment. Now we will discuss what dataset we have fed to Llama 2 model. We have used Australian credit card dataset, which is a valuable resource for financial data analysis. The dataset is available at UCI repository. It has 14 attributes. Some are numerical and some are categorical. All the attributes are masked for the confidentiality of the customer. Now we know what is the Llama 2 model and how we can use it for prediction and for the generation of embedding. Next, I would like to hand it over to Pat and she will discuss the results of the experiment. Thank you.
Thank you, Shikha. Hello, everyone, and thank you for attending this presentation. My name is Pat Bhattacharya, and I will take you through some of the results that we got. As Shikha mentioned, we worked with the Australian credit card dataset and built a Llama 2 model. The Llama 2 model gave us two types of outputs. One was the predictions from the model, which classified each observation to identify the defaulters versus non-defaulters. The other output from the Llama 2 model was a set of 35,000 embeddings. We had two types of goals with the outputs of the Llama 2 model. First, we wanted to look at the performance of this Llama 2 model and understand how well the predictions worked as compared to the traditional credit risk models. The second thing we wanted to see is whether we could use these embeddings from the Llama 2 model and whether those would help us build an even better credit risk model. Therefore, we decided to conduct 4 different experiments, which I have outlined on the table in this slide. So the first experiment was purely the Llama 2 predictions. This is shown on the first row of the table and is called case 1. In the other 3 experiments, we built logistic regression models, and I will explain how these differ. In the second experiment, which is depicted as case 2 in this table, we decided to work only with the embeddings derived from the Llama 2 model. As we saw, the Llama 2 model gives us 35,000 embeddings, and we decided to try and use some of these embeddings. So we built a logistic regression model with only these embeddings as the independent variables in our model. In our third experiment, which is depicted in this table as case 3, we decided to work using only the original Australian credit card dataset that was given to us. So the variables that were there in the original dataset were used as independent variables in a logistic regression model. In the fourth experiment, we decided to combine the second and third cases. And this is shown in the fourth row of the table and is called case 4. And so this time, the original variables as well as some of the embeddings were used as independent variables in the models. For all of these experiments, the main dataset was split into train, test, and validation datasets, and the same splits were used in all of the experiments. The dependent variable is, of course, also the same for all the experiments. It is the independent variables that were different for each of these different cases. Another thing I would like to mention here is that all the models were built to regulatory standards. So we dropped variables from the model if they were too highly correlated with the dependent. Also, if any of the variables had high correlations with each other, we dropped one of them. We needed some sort of measure to compare the performance of all of these different models. We decided to use area under the curve, or AUC as it is often called, to evaluate the performance of these models and compare them with each other. The advantage of AUC is that it provides a single value which represents the model's ability to distinguish between positive and negative classes. And models with higher AUC are considered better in their ability to distinguish between positive and negative cases. By definition, the AUC value lies between 0 and 1, where 0.5 depicts a random guess and 1 depicts perfect classification. I will now show you some of the results. We already had the Llama 2 model predictions, so we went ahead and calculated the AUC values for those predictions. We found that the AUC in the trained dataset is very close to 0.5. This means that the Llama 2 model does not perform any better than random in the trained dataset. So if you or I were to randomly guess who is likely to default, we would be as likely to be correct as the Llama 2 model. The AUC values in the test and validation datasets were slightly higher, but not by that much. So the original Llama 2 predictions were very weak. We will share some thoughts on why this did poorly once we have gone through the results of all the cases. The next experiment we conducted was the Llama 2 embedding logistic, where we used only the embeddings from the Llama 2 model as independent variables in our model. The AUCs are shown in the second row of this table here, and as we can see, the AUC values are much higher, which means the model is performing much better than the pure Llama 2 model. One thing I wanted to mention here is that even though we had 35,000 embeddings, we did not actually need to use all of these embeddings to get this improvement in performance. We actually went ahead and inspected these embeddings, and based on their relationship with the dependent variable, we chose only the top 35 embeddings to build our model, and that already gave us these good lifts. We wanted to compare the results from the embeddings only model with our traditional logistic regression model. And so the next model we tried was our traditional logistic regression model, where only the original variables in the dataset were used to build the model. The AUCs for this model is shown in the third row of the table, and we can see that the traditional model definitely performs better than the pure Llama 2 model. Moreover, when we compare the AUCs from the traditional model to those from the embeddings only model, we can see that the traditional model performs better than the embeddings only model across all three samples. Therefore, up until now, while the embeddings only model looks promising, there is no real reason to use the embeddings. This brings us to our last experiment, where we tried to use the original variables as well as the top 35 embeddings as independent variables in our model. The AUCs for this model is shown in the last row of this table, and we find that this combined model performs significantly better than all the other models across all samples. Next, I will hand it over to Krishna, and he will take you through some of the interpretations of the results and so also talk about what comes next.
Thank you, Pat, for those most interesting results. So, once we got these results, as a team, we started, you know, thinking about it as to why we were seeing what we were. And the first question was, why is the Llama 2 model directly doing so badly? And, our thoughts were that the model is general. It's focused towards financial services, but it is geared to solve a lot of different types of problems across different kinds of firms, and not just credit risk for this particular firm for whom we had the data. And so uh, kind of the credit risk impact got diluted, and that is why it was not doing as well. And then the mass attributes and the limited number of attributes did not help either. So that was our conjecture. Uh, the next question which we thought about is why the embedding model works. So the embeddings are essentially taking the predictors and creating some span across them, combining them in a way that is uh, meaningful and from the Llama model's perspective. Now, uh, when we are bringing it to our logistic regression environment, uh, among the thousands and thousands of embeddings, our algorithm is picking up the ones which are relevant for this use case and training the model on them. And that is why it works well, because of those large set of embeddings, we're picking out the ones which work well for this use case and then focusing the estimation on those. Okay. So then another question which came to our mind and which we thought about is that why does the traditional model outperform the embeddings? And you know, at the end, the embeddings are derived from a general LLM model. Yes, there are a lot of them, and so we were able to pick some which work for within the logistic regression environment. But then they are it's not the same as taking the raw predictors and using them directly to create use feature engineering there directly to create something which is just specific for our problem, the use case we are doing, and this data. And some of the nuances are being missed even by the general model, even with the large expanse of embeddings. And that is why we are uh, getting the traditional model to outperform. And then the question comes, why does the combined model work the best? And I think it's an ensemble type effect. If you have two types of models have with different strengths, when you combine them, the end result is stronger. uh, uh, we get a lot of context from the traditional model. It focuses on the problem at hand and does a very good job of optimizing for the data we have. And what the um, llama model embeddings are doing is they're kind of tempering this by and augmenting this by adding a voice of moderation, like, okay, this is the data, and you you're just focused on that, but there are things they do not see in this training data, and that uh, might be relevant, and the general wisdom of learning from the greater mass, which kind of tempers and prevents this model from almost overfitting. It's almost like what an industry score would do. So these were our conjectures. We would love to get your perspective on this. So please use the Q&A in board to give us some thoughts as well. So what is next for us on this project? So we definitely want to replicate this experiment on other samples. And we are not just saying credit risk. Uh, we want to expand it to fraud and collections. In fact, we have started working on a fraud problem, and we are very interested to see what the results come out there. But beyond that, this experiment, we were looking at traditional data, and we were just comparing algorithms, how the generative AI algorithm compares to mm, traditional algorithm when they are given the same data. But there is this opportunity to incorporate non-structured data and really add some extra juice to our credit risk scorecards. And that's something we want to experiment with as well, and see how much extra potential we have there. And in all of this, we are looking for new partners. If you think this excites you and your organization would like to be part of these experiments, work with us, and join the next series of experiments we do, uh, or otherwise work with us, please feel free to reach out to us. Thank you so much for joining this presentation. We will now open up for the question and answers. So just please use the question and answer board to uh, let us know your thoughts, comments, and queries.